So part 3 is going to deal with an application of rate laws, and that is the idea of half-life. You have learned what half-life is already. Half-life is the time required to reduce the initial concentration of something to half its quantity. We saw that when we were taking a look at radioactive isotopes. The half-life of radioactive isotopes is one very good application of the idea of half-life. So once again, half-life equations are obtained through rearranging the integrated rate laws. And so here's the ideas for the half-lives for the 0, 1st, and 2nd order. So notice that for 0 order, so t to the 1/2 is the half-life, so it's the amount of time that it takes. For a 0 order, you've got the initial concentration divided by 2 times the constant. For 1st order, it is simply the natural log of 1/2 divided by k, well, the negative of the natural log of half divided by k. Well, the natural log of 1/2 is 0.693. So notice for 1st order, the concentration is actually not an issue. The half-life is whatever 0.693 divided by the rate constant is. And then for 2nd order, the half-life is 1 over the concentration of A times the rate constant. So for radioactive particles, they are only considered 1st order. But let's take a look at just a generic chemical reaction first. So the half-life for the 1st order reaction is 2.4 hours at 30 degrees Celsius. If we start with 100 grams of N2O5, how many grams will remain after a period of 16 hours? So what we want to do first is solve for K. So t to the 1/2 we know is 2.4 hours. The half-life is 2.4 hours. So K is actually equal to 0.289 once you take this equation and rearrange it. Okay, now that we have K, we can solve for A using our equation that we have for the 1st order half-life. And we wind up with the concentration of A being 1 gram. For radioactive decay, again, it's a 1st order example, so the rate is always equal to the constant times the number of radioactive particles. So 1st order equation, you can express it like this. The stuff I have at time t, the stuff I started with, take the natural log of that, and it is equal to negative kt. And where k is equal to 0.693 divided by the half-life. So I've given you a couple of different equations for half-life. So these two are one way of expressing it, but I think we actually, I gave you something else earlier in the year, so we can look at that as well. You can use these equations to find numbers of half-lives, the amount of material remaining, the amount of decayed material, or the time. So for example, from 1 gram sample of strontium-90, there's only 0.953 grams left. After 2 years, what's the decay constant? What's the half-life? So K is equal to negative 1 over T times the natural log of an RT. So because we took that first equation and rearranged it, find out that the decay constant is 0.0241 years to the negative 1. So then we can plug it into the half-life is equal to negative 0.693 divided by the constant. You get 28.8 years. Another example, what quantity of 500 grams of strontium-90 will remain after 100 years? The last example gave us the rate constant, so we want to pull that in and use that same rate constant from before. Where is it? There it is. Plugging in what I know to find out what I don't know. The amount of time, or the quantity I have after the 100 years is 44 grams left. So these are pretty straightforward. All right, so that ends that second video on half-life. So again, there's a couple reactions, a couple equations in there. Let me go back. There's a couple equations. This is one of the nice equations. And then you have the t to the 1/2 equation as well, relating to the constant. Usually half-life problems are going to be first order. You rarely see any questions about a 0 order or a second order half-life reaction. So this is the stuff that you're going to use most often. All right, so that ends our discussion of rates. Like you saw, the next slide is something a little bit different. We're going to start to get into mechanisms in the next videos we take a look at.